your hand if you see my hand raised. Okay, please raise your hand. Okay, good. So, in the first half of the talk, we kind of, generally gave you some examples of these pattern families in spatial data and motivated in terms of a few use cases. We also looked at a few concepts from traditional statistics like autocorrelation and heterogeneity, which motivates us to look at some new kind of statistics called spatial statistics. And then we finally talked about one pattern family which had to do with location prediction. Now in second half we are going to look at three more pattern families. Let's start with hotspots. Okay. So in this segment, we are going to actually compare with classical methods of clustering and then the new spatial clustering or hotspot. And in particular, right, first day I do remember, how many of us know k-means? Okay, a lot of us. So in classical data mining or statistics, if you have to do clustering, just like regression is for prediction, k-mean is the most popular clustering methods. But there are other clustering methods as well. But at least since most of us know this, I will contrast this with SAT-scan. Okay. All right. So let's start with a quick review of k-means. It's often used for a set of points. So here, suppose I am giving you a table which has 6 rows, and there are 2 attributes. And I'm asking you, can you think of natural groups of these records? So could you please, take a look and say, if I want to make 2 groups, how would you partition the data? And I'll close the door. Yeah, can you actually stop, tell me visually what the groups are? Okay, BC looks similar, okay. BC and F, oh, very, very nice. So a lot of you have a good spatial visualization, But essentially, if you put it in a 2-dimension, at least for 2-dimension, you can see that if I plot it, you kind of see BCF are together and ADE together, right? In higher dimension, it's not easy to do that, and that's where you have algorithms like k-means. And k-means is a partitioning algorithm, okay? So the way k-means work, many of you know that you can start with some seeds, right? So k is specified by the user, and the seeds, you can randomly pick 2 data elements, okay? And there are smarter seed selection methods as well. So suppose, for randomly I pick these 2 to be the seed, right? Then k-means goes through 2 steps iteratively. In the first step, it assigns the remaining data points to the closest seed, right? So you can guess that B will become red, right? And these will become green. So this is your first step, that you made 2 groups based on the seeds at hand. So this is your initial partitioning. But as we can tell, this was not a great partitioning because we randomly chose the seed, right? So now you revise the seed, right? So based on this partitioning, you replace the seeds by center point of the groups, okay? So the red group, the center point will be somewhere here, right? Green group, the center point will be somewhere here, right? So in the next iteration, we revise the seeds. So now these are the 2 seeds, right? Okay. And then we repeat the process. So with the new seed, we again recolor the data. And do you see, will color of any of the points change? Okay, C looks closer to the red seed, right? So if I recolor things, then this is what it looks like. Now you have more or less gotten your groups, but the process hasn't really ended. Okay, the way it ends is to say, okay, let's revise the seeds again. Okay, since there was a change, see the changed color, it's possible more changes can happen. It's a greedy process, right? It's a greedy descent. So you recolor, okay, recolor the thing. This case, will any of the colors change? Okay, C is, this was the closure, right? But in these are the closure, right? Okay, so this case, nothing changes, and then you revise the seeds again, and your seeds are now stabilizing. And in the new partitioning, nothing changed. So you have conversion, you will stop. Okay, that's what k-means does. Okay, this was proposed roughly in 1950s, and it has taken off like wildfire. Everybody uses it. Okay, even though it's a heuristic, it does not give you many guarantees. It's very easy to fool k-means, and you will see how spatial data fools it. People don't know very many properties of k-means, but everybody uses it. Okay, oftentimes people don't even visualize the data. They take k-means on faith. Okay. So let's try to see what happens if I use k-means for spatial data. Okay. So, all right. So limitations. The biggest one in my mind is the following. You know, a lot of applications in space have major societal significance. So when you make mistakes, the costs are very high, right? And k-means gives, you give it input, gives you an output, but it does not tell you anything about quality of the output. Like in regression, at least you have R square. How many of us remember R square, right? So many of us. So regression is same thing. You give it input, it gives you an output, but it also tells you whether that output is meaningful or not. The R square can tell you that regression learned nothing. It was just a bunch of random points. Regression came up with coefficient, but the R square was really, really insignificant, right? In k-means, can you tell that? Does k-means tell you that, for example, I can give it a set of points which are all together, and I get k equal to 2 or 3. It will make partitions which are all very close to each other. Or I can give it set of points which are really naturally very separate. Does k-mean tell you that in one case, the clusters are very nicely separated and coherent, in other case they are not, right? So the sum of the distance from that, right, which will give you the coherence of the cluster, right? And then you have to look at the distance. But those also have to be normalized with respect to your dimensions and so on, right? So you have to actually do a lot on your own. You are pretty much on your own. K-mean is not giving you a measure saying these are good clusters and these are not, right? Even the choice of k is a problem, right? So let's try to see if I throw it, k-means to data set which I know is random. Okay, so this is complete spatial random, but k-means would still give you some partitioning, right? Whereas in a spatial statistics, I want to say, look, whatever you did was not very meaningful, right? It was just by chance. Okay. All right. This is sort of the clustered data, and here, some of these things are interesting. And remember this data? But k-means will give you something. How meaningful is this? You could group it in many different ways, right? This is actually declustered. This is not clustered. This is declustered. But k-mean is giving you something which is, I don't know what it means. So this is a problem. You need to augment k-means with a lot of things and deal with it. Okay. Certainly, if I am looking for hotspots, are these really hotspots? Right? There are like these may be hotspots. Here also you might see a little bit of dense area in a complete spatial random, but they are probably due to chance, right? Okay. So the use case is different, and at least National Cancer Institute came up with this technique, scan statistics, because in that space, if you declare a place to be cancer hotspot, there are ramifications. You have to go do environmental investigation. And people will have lawsuits. There are all kinds of things. People will not want to live there. Things happen. Okay. So let's take a look at how this works. Okay. So this is essentially a hypothesis ranking technique, and it uses a few statistical measures to try to give you something like a R square. Okay. And there are two different measures that are being used, and the idea is to get rid of these chance clusters. Okay. So these are sort of the step. You first enumerate candidate zones. So this is one sort of, hypothesis generation step, okay? And these hypotheses are spatial areas. So to be more precise, SAT-SCAN will enumerate circles, okay? To be even more precise, they enumerate 2-point circles. So if you give it n points, it will make pairs, okay? N choose 2 pairs. For each pair, it will put 1 point at center, other point at circumference, make a circle, okay? So then all those n choose 2 circles will be put through likelihood ratio test. Okay. So and then any circle which meets a threshold on likelihood ratio would be retained. And so this is, and I'll tell you what this measure is. And for those circles, you now actually test significance by actually generating complete spatial randomness data 100 times, 1,000 times, and see how often complete spatial randomness can give me this likelihood ratio that I am seeing in the data. Okay. If you can see that often in complete spatial randomness, then you are saying, okay, you got some dense areas, but it's probably due to chance. Don't worry about it. Okay. So these are the two measures. Okay, so let's go back and look at what is this likelihood ratio measure. So this is actually comparing two hypotheses. Okay, so one hypothesis is that inside the circle what I am seeing is complete spatial random, and the other hypothesis is that it's clustered. Okay, and then you look at the two probability and take a ratio. So how much more likely it is to be clustered than it is to be complete spatial random. Okay, so this is one way to do the ratio. Another way to do the ratio is inside and outside is another way. Okay, but you're looking at essentially two hypotheses and you're ranking it. So you're always concerned about chance pattern, and you're looking at every pattern to see how different it is from chance. Okay, and that's where the strength of statistics lie. Okay, and by the way, this kind of analysis is also a critique of vast majority of machine learning. Machine learning often starts with the statistical method, and the first papers do have these things, but then computer scientists get excited and they drop this and they want to speed up things, and then they create things which can create a lot of false positive. Okay, so you, even in those techniques like SVM, right, or deep learning, ask them this and figure out if they can give you any of that. And if they cannot, then the use case you want to be careful. It's okay to do clickstream mining and add and soft things with it, but you don't want to be doing crime hotspots and cancer hotspots with those. Okay. In fact, one story that I alluded to yesterday at TCS is Google flu trends. How many of us have heard that story? Google flu trends. Okay, not many. So let's not worry about it. Google's deep learning stuff was applied to public health and they failed miserably. It was a big embarrassment to them. Okay, just be aware of that. All right. So this is the method, and let's go look at a few data sets to see what it does. Yes. Okay. Everything okay? Okay. So let's suppose I apply SAT scan to a complete spatial randomness. Okay. So in the first phase, it does actually pick up the circle which has highest ranking, and in this case, this ends up being the circle. You see this pair? One point is at the center. This is the circumference. So among all the point pairs that you can apply, this pair, and you might even actually see a little pair here, couple of them will come out with high likelihood ratio. Okay, but once you test for p-value, in this case p-value is 0.128. So there is 12% chance that this happened due to just randomness. Okay, and for most statistical tests, that's not unacceptable, right? Usually you say less than 5% chance, or less than 0.1% chance. Okay, so this one would be rejected in the second phase. Okay, you can ask yourself what will k-means do with it, and remember we saw that it will give you something, but it won't tell you whether it's significant or not. Okay, computer scientists may know of other schemes which gives you density-based clusters. So can anyone name anything other than k-means which gives you density-based cluster? DB scan, some of you remember. And you may want to ask what will DB scan do on this. Okay, DB scan first of all has two parameters, that the neighborhood range and the epsilon, and based on that parameter it will give you different things. But again, it will not give you statistical significance. Okay, that's the main problem. All right. Here is another data set. It's a little lighter, but you can see lots of dots all over the place. So this is a CSR, and then we have superimposed a dense area. In this case, this is the circle, which is the highest likelihood, and then you test the p-value, and let's read it. 0.001. So your second phase tells you that the chance is less than 0.1% that this came out because of chance, and that's usually considered acceptable, right? Yeah. So this case we will find it. DB scan probably would also find it, but it will not give you significance. That's the difference. Okay, so this is sort of your basic review of SAT scan. I hope that gives you some contrast between the techniques. And key thing is you want something like a R square, for your clusters, and it is completely missing in the literature on machine learning, data mining, and so on. And that's why you want to go to techniques like SAT scan. If your domain is such that false positive costs matter. Okay, if you are showing advertisements on the web, what's the cost of showing the wrong advertisement? Not much, right? 1/1,000,000th of 1 cent. And even if you showed a wrong one, you have millions of people coming every day. So after an hour or two, you will know that you are not making any money. So you will self-correct, A/B testing. So that's okay, but that's not the nature of cancer data or crime data. Okay, once you make a mistake, you get a really bad name. Okay. All right. So next, I'm going to show you, what's happening beyond that. And again, day one, I was showing you a little bit of this. So there are other domains where you have more domain knowledge, right? So instead of circles, you are maybe looking at donut holes, or you are looking in urban areas, you're looking at roads and so on. So there are newer methods where, if I given you this data set, so instead of looking circles or ellipse, the methods can give you these linear hotspots, or they can give you rings, okay? And then these are sort of happening in current thing. So let's again pause a minute and think about this. Okay? Okay, what is false? So how many vote for A? Okay, B, C, okay, lot more, and D. Okay, good. All right. So that was one message I wanted to bring up. Okay. Again, one other thing you should know about this space is k-means may have other uses. Okay, if you want to partition the data, so I don't want to discourage you from using it. Do the k-means, look at what it is doing, but at least visualize the output. So when you look at things, you will often know whether k-mean did sensible thing or it gave you something that's nonsense. Okay, and that's the ultimate test. Always look at your data, visualize it, and look at it. Even SAT scan is not 100% perfect method. Remember on day one I was showing you the Legionnaire disease in New York. If your data is very sparse, SAT scan may not find things. It's possible. Okay. So there are, if you use SAT scan is a public domain software, you can download and try it, and we use it in lab a lot. And it does, once in a while gives you thing which does not make sense. Okay. So again, don't take all of these on blind. Okay. So take the output, visualize it, and try to interpret it. At the end, I will show you that life cycle. So you will also know that. Unlike SQL, okay, when you were in day one SQL, you were on much firmer ground. It was correct and it was complete and there was no mix up. Okay. But now you are in the space which is probabilistic. This is the space of Siri and Google search and stuff like that. So when you are in data mining machine learning, you are going to have false positives and true negatives. Okay. Just that based on your domain, you want to have some additional checks and balances to figure that out. Okay. And if your domain false positive costs are very high, one defense is to check for statistical significance. But it's not foolproof. You can still find things which are statistical significant, but they may not be interesting. Okay. Like in case of cancer, when you run the first test, you may see, okay, there is a geographical hotspot of some kind of cancer. So US, if you run it blindly, not understanding the data, lot of cancer hotspots will show up in Florida. Okay, then you show it to a public health person and they say, not interesting. Why is that? Because all the retirees go to Florida. It's an older population and lots of cancers are common in older population. Okay, so they say, okay, go back and adjust it for the age. Okay, don't just come back and tell me old people live there. I know that. Okay. So you redo your data and you do your hotspots, and now they may shift to Appalachian, and you go and show it to them and say, not very interesting, because that's, they know that its income is low and there's a lot of smoking. So they say, okay, go back, adjust for smoking. Okay, and come back and tell me if anything is left. Okay, and so on, right? So each domain, people do further kind of validation, and that's something you should be aware of. Okay. All right, let's go to another pattern family, spatial outlier, the discontinuity, and see how we're doing it. Okay. All right, so in this one, as I said, we are going to talk about a few tests to detect that and contrast the global and spatial more formally. So this is the example we had early on. Remember the traffic data. This is space, one-dimensional space, 60 sensors, and this is time of the day. And what we were looking for was this sensor number 9. So let's try to see quantitative test how we can pick that out. Okay. So one way to first start defining spatial outlier is to think about this, let's say, linear space, which is easier to visualize. And suppose you have an attribute value on that space. So this could be the traffic volume for different sensors. And suppose over space the variation looks like this, okay. So in this variation, you can contrast the global and spatial outliers, okay. So things like the maxima and minima, minima, they are global outliers, particularly if they are far away from mean plus minus few standard deviation for normal distribution, right. The spatial outliers are something like this, where you see very different from the neighbors. So they are more like discontinuities, okay. So, and many data sets, they are distinct things. So this one, as I told you, if I ran global outlier test, that's not going to separate it because there is lot of similar color, okay. So, but you want to test for the comparison with neighborhoods. So compare this sensor with the neighbors. Alright, so let's try to at least see how you do that if the measurements were not time series but a scalar. Okay. So one of the classical tests is variogram. It's a visual kind of test. It takes the data, summarizes in a form that allows humans to see that. Okay. So in variogram cloud, if I have this data set, you transform this in a new space. So if there are n points here, you kind of make up to n choose 2 pairs, okay. And then you put in this space where x axis is for each pair, you say in geography how far apart they are, okay. Simplicity, let's say Euclidean distance or something, or network distance. And on the y axis, you look at attribute value difference, okay. So if I am looking at s, let's say PS and PQ, look at geographic distance is very small, right? But attribute distance is large. So that's why they are sitting over here. Small geographic distance, large attribute. So they are sitting in this space, right? So this visualization, once you have done that, you can possibly even fit a linear regression line, right? Which will sit somewhere here. And then try to see what pairs are very far away from linear regression line. And then you have to make a manual effort to say is there anything interesting about these pairs, right? And in these pairs you see they are P, Q and S are involved. Should I declare all 3 of them to be spatial outliers? So how many think yes, all P, Q and S, all 3 are spatial outliers? How many think P is a spatial outlier? How about Q? Few, okay, how many S? Lot more, right? So a spatial outlier, this is a problem, as they tell you when you make friends, be careful, right? Because a bad character influences you. So here notice the score of P and S went up P and Q went up because of S, okay? So in spatial outlier, what you do is always take out the most offending item first. So you look at all 3 and say, okay, S is showing up again and again and again. So take S out, that's the first outlier. But when you take S out, these both pairs are gone, right? Score of P and Q will change. So if I take S out, what do you think? Are P and Q likely to be spatial outlier? No, it's now a very smooth curve. So you recompute, okay, and so on. Alright, so this is one test, variogram cloud, which is widely used for summarizing and looking for discontinuity. Alright, let's next go to another test. It's called Scatterplot. Again a visual kind of method which kind of puts your data in a new space. So same data set, but this space is slightly different. So here what we are doing is to map, so every point here, n point here, then you have n point here. So let's look at for example S. Okay, so S over here from location and attribute value, I have mapped it to what's the value of attribute of S, okay, which is very large, okay, S is very high. And then what's the value of neighbors of S? So this is the average of, in the neighborhood of S, if I look at these 2 values, this is sort of the attribute value, which is kind of low, okay. So each point is mapped to this new space, attribute value in neighborhood, attribute value at this point, okay. So you are kind of doing a derivative kind of business, alright. And once you have done that, again you can put a sort of some kind of linear regression line and see which points are really far away from this line. Then as you can see in the vertical distance, S is the furthest. Even P and Q look a little bit high, right? So you take out S first. And when you take out S, will this plot change for any other point? P and Q will change because their neighborhood has changed. And they would actually start to drop closer to the line. Okay? So again you do it one at a time. Okay? So it could be expensive, and that's where a computer science challenge is, can you figure out a way to reduce the iterations without affecting the result quality? Okay? So everyone comfortable with the second test? Right. Okay, let's look at another one, and this is now called Moran Scatterplot, which is a slight variation. So in this space, we are normalizing things a little bit. Okay. So again, endpoints here, you go to endpoints here, and you're looking at attribute value of a data and attribute value in the neighborhood. But the main difference is now we have normalized it. How many of us remember what is z-score in statistics? Yes, okay. Right. So you take your value, subtract mean and divide by standard deviation. So you're assuming it's normally distributed. And by doing that, you have some advantages, right? So the previous test and this test are really same. One is using raw value and one is using normalized value. Okay. And then you put this line and say, okay, S is the furthest. Okay. Take it out and then recompute value for the neighbors, and they are more likely to drop back to the line. Okay. Any questions, issues? You are comfortable with this? Okay. So I'll show you one other test which is even more direct. And this test is what we call Z test. So here instead of visual in comparison, we are actually going to combine the value. So what we have done here, we left the location space here. Okay. And on the y-axis, we took we did the following. So you look at the attribute value of S, okay, and take the difference from the neighborhood average, okay, and then you normalize the difference. Does that make sense? So you are sort of in that derivative space, so to say, difference space. So for every point, look at its attribute value, look at the attribute value in the neighborhood, take the difference. So that's your first step, right? So all of these locations, now I will have a basic difference from the neighborhood. But I don't want to use the raw score. Then I normalize it. So I'd say, what's the mean difference? If for every point, what's the average distance from the neighborhood? What is the standard deviation? If everything is normal distribution, standardize it. Because now I can interpret these numbers very, very easily. So for example, S is, look, it's even above 3. What it is saying that for S, the difference from neighbors is 3 standard deviation of the mean, right? If everything were normally distributed, that's very, very acceptable test for outliers, right? P and Q are just under 2, and obviously if you take out S, they would even reduce further, okay? But in this case, for example, you could, just look at very simple normal distribution like tests. All right. So it's another one. Okay. Questions in this one? Okay.
How can we compare these 4 tests?
How can we compare the forces? That's a good question. They would have different strengths and weaknesses. Okay. For this test, clearly the normal distribution is the assumption. If your data is not normally distributed, all this is nonsense. And same is actually true about the previous test. Okay. So anytime you are normalizing with mu and sigma, distributional assumptions come in. So you better test if your data is normally distributed. Okay. And this test actually came out of the same traffic map I was showing you earlier. And in the paper, you can go look at the Security 2004 paper. We tested the traffic measurements actually were normally distributed. And then you talk about the difference with the neighbor, and it will be normally distributed if your neighborhood size is fixed. So there is a theorem, if you add up set of normal distributions, you will get back a normal distribution. Okay. But if the neighborhood size varies, then it will be in trouble, right? So very rigorously all those assumptions were checked. And for that data set, this was a quick test to do that. But if your data set does not follow normal distribution, which of these tests can you still use? Yeah, the ones which did not normalize your data, right? You can go back to them. Also remember, the visual methods actually have a lot more information. Here, by normalizing and all that, we are sort of making assumptions, shrinking the information. So again, let me give you a meta level answer to this. How many of us know unsupervised learning and supervised learning distinction? A lot of us, good. So is outlier detection supervised or unsupervised? Unsupervised, we all know that. So main thing to remember is in unsupervised learning, There are no consensus way to rank things. There are a lot of opinions, and that is fine. But there is no way to compare things apples to apples. So best strategy in unsupervised is do multiple of them and look at them together, and you will get different information out of it. Okay. Same thing, hotspot detection. Is that supervised or unsupervised? Unsupervised. So that's why I will never say that SAT scan dominates k-mean. Use SAT scan and never do k-mean. No, it's nonsense. Do them both and look at both of them and interpret. Okay, they are different. Linear hotspot, circular hotspot. One does not dominate the other. They are different way to summarize the data. Do them both. Okay. If you are in supervised world, then you can look at those metrics, whether it's classification accuracy or F-score. So there is a way to rank things little bit better. Okay. Does that help? Yeah. Okay. And particularly if you are working with a scientist, that's how you want to approach. Give them multiple visualization, because they will see look for different things. Of course, you are in a computer science conference, they love to rank things and do things, but I don't think it's very smart. Yeah. Any other questions, issues here? Yeah.
So for a soul data, that is log normal.
Okay.
So if I have to check the outliers in the log normal data,
Right.
so which one would this take?
So okay, so could you just define what is log normal for people who are not familiar with it?
At the log, it is normal, column, this is the lower thing. So
Good.
size, atmospheric aerosol is the
Good. So original data is not normally distributed, but if I take the log of attribute for every point, I do get a normal distribution. Okay, so everyone knows what log normal is? Okay, so which of these techniques are first applicable if your data is log normal? Can I use this method for log normal data? How many think yes? How many think no? Okay, how will you use this technique for log normal data? You first take the log, right? You take the log and it brings you to the normal distribution, right? So you can use all 4 tests, but in order to have apples to apples comparison, maybe you want to use the first 2 tests using raw data as well as log data, and the last 2 tests using the log data. You got now 6 things to look at, right? So in some sense you are lucky that after log it becomes normal, but there are many data sets where even after taking the log it's not normal, right? Heavy tail distribution and so on. Then you have to go back to the first 2 tests. Yeah. All right, any other questions, issues on that? So in statistics, they have come up with all these transformations because, Gaussians is a bread and butter of statistics, right? Once you can come to Gaussian or normal, a lot of things can be done. And that's why they always look for transformation, that even though the original data is not satisfying the assumption, but with some transform, you can bring it back. Okay. All right, good. All right, let's. So this is, one other interesting computational result in this space, that if you look at the computational structure of spatial outlier detection, so I'm just going to basically tell you the result. It turns out that the result is essentially a spatial join. Okay, that's basically the W matrix is what you're using, and as you know, spatial databases have optimized spatial join very well. Okay, so these tests you can actually perform on very large scale data if you have access to SQL with OGIS library. Okay, so that's an interesting insight. These tests are very much within the SQL realm. Okay. All right, but again, there are other things we need to do. If there are many spatial outliers, then the computation cost goes up. One at a time, it keeps adding up. So people are thinking about how to deal with those in a more computationally efficient manner. Also, the test I showed you was using single attribute, right? If you have many attribute, how do you talk about outliers? Scaling up and so on. Okay, so let's do one review question when we go to the next space. Okay, how many vote for A? Right, B, C, D, All right, let's go to one more pattern family. And here, we are going to talk about collocation, and its closest analog in the traditional world is association rules. How many of us are not aware of association rules? Okay, just one. Okay, so we'll very briefly review it and then contrast. And try to get a little bit inside collocations. Okay? So association rules, this is sort of the classical story to motivate it, the diaper beer example from Walmart. But you may be surprised to know that actually its factual accuracy has not been verified. Some think it's urban legend. It's not a true story. But nonetheless, this has been told so many times that it looks like it. On internet, as you know, fake stories also take credence. So this case, we don't know whether it's a fake story, a true story. But you did see a true story in the video we showed you in the morning. Can you give me an example of association rule that the video was talking about? Remember the Australian TV video? What was the association that was used? It's exactly from Market Basket, retail data set, and that is a true story verified, and it has to do with Minneapolis. This company is headquartered in Minneapolis. What was that story? It was a little bit offensive possibly to some people.
About the pregnancy one they have to.
You still remember that story about pregnancy detection? So it turns out that there are certain type of creams, skin creams, which people during pregnancy often buy, and that's the association. So it's a similar kind of analysis. Okay, so let's try to think about what they do here. So here are, the first customer came and bought these things. Second customer came, bought these things. Third customer came, bought these things, and so on. So looking at this transaction data, this was the main consumer behavior data which was available in 80s and early 90s. This is before the web. Once you are in web, we can see a lot more of your behavior, right? If you're on WhatsApp, we know a whole lot about you, right? Or Facebook and so on. But this is the original customer behavior data, and it's still used heavily because a lot of money information is in here. So given that, they want to do something very interesting, which is called the loss leader strategy in retail. How many of us know what is loss leader strategy? Okay. So you have come across sales. Remember, a lot of items are put up on sale, right? Big sales, and at those items sometimes they are sold below the actual cost, so they are taking a loss. Why would a retailer do that? Right? They are not going out of business or anything, right? Why would they sell some items at a loss?
Better than keeping it as dead stock, because they may not be of use sometimes.
Okay, so that's a different strategy. That basically is with a seasonality. So every product they bring in, they say, okay, I'm going to keep it only for a year. So initially I mark it up with high profit, but last month or two I want to get rid of it. Okay, so that's a different strategy. That's a life cycle strategy. But okay, so if you take loss on one, what do you do on the other? You take the profit on the other. Okay, and there are different examples of it. For example, in US, the cell phones are subsidized, probably here too, but they make money on your data plan, on your minute plan, right? So there are a lot of examples like that. So in many cases, these pairs are well known, that if you buy one, you are going to buy the other. So they can sell you one on discount and make money on the other. Okay, but companies like Walmart wanted to ask that, are there other pairs which are not known to everybody? Okay, are there other pairs which people buy together, but people may not be aware, and most of their competitors are not aware, and could they extend the loss leader strategy to those pairs? Okay, that's where this came from. Okay, this is 1984, well before data mining was born, or and so on. So they wanted to analyze this and say, okay, tell me the pairs which are going together. And back then, obviously, data mining is not even there. So what you are going to use is statistics or machine learning. So if you knew statistics, how would you solve this problem? I want to know which items are bought together. Okay, this is the data. What would you do? Okay, that's 10 years later. Okay, in 1984, you don't know support, and there is no, statistics. In statistics, how would you model that? Okay, that's all association rule here. But in statistics, if I'm saying two things go together, what's the measure? Okay, so what's the measure which is well known? Correlation coefficient. Okay, that's the statistics. And that's a more accurate measure than all the association rules. Okay, So you may want to ask, why didn't Walmart use correlation coefficient or chi-squared? Because that's what statisticians will do, right? That's how you correlated smoking with cancer, right? That's how you actually correlated El Nino with change of weather elsewhere. You know, Britishers had hundreds of people sitting in Madras computing correlation coefficients, okay, 100 years ago. Why didn't Walmart use correlation coefficient? If I test these two for correlation, will that give me a significant correlation? It's possible, okay. If it is not symmetric, at least you will get conditional probability and so on. So this is where you start to see the trade-off between computational cost and statistical rigor, okay. Now correlation coefficient for one pair is not that expensive, right? It's linear in complexity, right? Asymptotic complexity is order of n. You scan the data once, just like linear regression, you can compute it. So what is going on here? And they had one of the largest computer on hand in 84, 8,000 node machine. And they concluded they could not compute correlation coefficient. Why? With 8,000 node machine, they said, I don't have enough horsepower to do it. Where is the NP completeness here? I gave you a linear complexity. So think about how many different items a store like Walmart deals with. You know, you probably know this number for Amazon, right? How many different items does Amazon deal with? Any guess? 1,000? 10,000? How many? 6 crores. 60 million, right? Place like Walmart would have fewer, but at least 1 million. How many pairs can you make out of 1 million? Million choose 2 is now 10 raised to 11, 10 raised to 12. Okay, that's now a big number in 1984. It's still a big number today. That's what big data is, okay? And then for each pair, how much data do I have to go through? How many customer transactions do you think Walmart gets in a week or in a month? Or how many does Amazon get? Millions and millions, right? So even to test one pair, I have to go through the million. Maybe I can do that in a second or two. But 10 raised to 12 pairs, I am in trouble, okay? So they concluded they could not handle correlation coefficient. But it was such an important business problem, they said, well, what can you do? So I know what you cannot do. And in theory, people really focus on that. But in systems and real world, they come back and saying, okay, tell me what you can do. I don't want to hear what you cannot do. And that's how association rule was born. They said, okay, we can't tell you quadratic interest measures, but this is what we can do. And that's the birth of association rule. They said, we can tell you the frequency. How many transactions have this together? We can tell you conditional probability. Okay, how often when I see diaper, I also see beer or vice versa. These are both linear measures, okay? So we can try to do that. And later on, this was formalized as a priori algorithm, 10 years later in 1994 by Rakesh Agarwal. And he basically said these measures have a very nice computational property called anti-monotonicity. What that means is that if I am looking at the support for this pair, it is bounded by the support for the subset, okay? So at least there are 2 out of 5 with both. So the number of transactions with diaper has to be 2 or more, right? And beer has to be 2 or more. So using this, you can do sort of pruning, and instead of going directly to the pair, you can first look at the singletons. And any singleton that does not meet the frequency threshold can be thrown away. And now you make pairs out of the remaining ones. So computationally, it's a nice measure. But statistically, there are lots of problems with this. So if you rank these pairs by support, and you rank the pair by Pearson correlation coefficient, do you think we get the same ranking? How many of us know that question? If a pair has very high support, does it mean the correlation coefficient is high? Does it mean it's even positive? Could you have a pair with high support and negative correlation? Actually, the answer is true. Okay, your support ranking has nothing to do with correlation ranking. So try to imagine how would the statisticians and people trained in statistics felt when in mid-90s this started to catch fire and everybody was trying to use it. What do you think they said? Statisticians were very mad, and they came back and said this is black magic. and they were extremely upset. There were very lively debates. Finally, David Hand in Britain was the first one who converted to the black magic. He was president of the European Statistical Association. So he tried to explain this to them, right? Then more statisticians came. So there was some truce, by the end of 90s and early 2000s. Now, when the big data came around 5 years ago, the same trade-off came back: computation versus statistical rigor. But this time, statisticians were not fighting, because they felt they missed the boat on data mining, right? They lost a lot of opportunity. So this time they turned around and said, oh, the science of big data is statistics. They wrote 5 papers in 1 year. Okay, they saw the light, and this time they want to work together. But anyway, this has a very colorful history in 1990s. Okay. So as I said, the algorithm, I don't have to tell you much, but basically, if let's say this is the transaction, and you want all the pairs above this, there is you first actually look at the singletons. Okay, and at this level you can start pruning things. So out of these 6 items, which ones fall below 50% support? These 2. So you throw them out. Instead of making 6 choose 2 pair, I only make 4 choose 2 pairs, right? So these 2 are gone, and then you make these only 6 pairs instead of more. And for those 6 pairs, I again look at the support, and I can start throwing out more pairs, right? These 3 are gone. And for making triplets, I only look at these 3. And now there is a second pruning that goes on, which actually says I don't even have to make triple out of it. Why is that? There are some items remaining, but there is a second pruning goes on which says no triple is going to make it. And because if a triple can make it, all of its pair subset should be there. And notice that is missing. So if I think about milk, cookie and juice, if that triple may have survived, then I should be seeing cookie and juice above the threshold, and I don't see that, right? So anyway, there is very nice pruning, and you can handle this nicely. So even though worst case asymptotic complexity is exponential, for many real world data set, these algorithms do really well, and they behave. Okay. All right. So that's good news. And as I said, by mid 90s, this was in commercial space. Every retailer was adopting it. There was software. IBM was launching consulting. So the question is, can we use it for spatial data? People wanted to use all of this for spatial data. And the big question now is, spatial data, transactions are not natural. Okay. So you can force feed a transaction. You can divide spatial data into districts or counties. But remember that the neighborhood edges, some of them will be cut by your partitioning. So you will lose information. And whatever you will find will not relate very well to things like Ripley's cross-check function. Okay. If you don't care about that, you can go ahead and use it. Many people do it. But people who are more sophisticated would not really like your result. Okay. So anyway, this is non-trivial. So I'm just going to go the solution. Let me just skip this part and just show you collocation. Okay. All right. So collocation, this is how it is formed. Okay. So you are given a set of features very much like the item types, and you are given these instances. So A, for example, there are 2 of them. B, there are 2 of them, and so on. And we are looking for these subsets which interact. Okay. So one way you can find them is to run Ripley's cross-check function on every possible pair. But you are going to face the same dilemma of Walmart. Okay. It's very expensive to do that. So we are looking for some new measures which have better computational probability. And this was done as a thesis in our group about 2003. So these are the measures, and these were defined essentially on neighborhood graph. So first measure is, this is a conditional probability measure. We call it participation ratio. So I'm basically saying, okay, tell me what fraction of A participates in this pair. Okay, and it essentially means, so there are 2 A's, and you notice both of them have B in the neighborhood. Okay, so this is the probability. If I see A, what's the probability I will see B nearby? Okay, so in this case, what will be the answer? 1. Anytime you see A, there is a B nearby. Okay, I can ask the reverse question. If I see a B, what's the probability I see an A? This B, okay, does see A, this one doesn't, right? So half. And then we try to bring it together to call it participation index. It's the minimum of the 2. Okay, some of you may recognize minimum. If you know your algorithmic game, minimum is what gives you that anti-monotone property. Okay, so this is a computational game that's being played here. Okay, But by doing this, you have increased the separation between Ripley's cross-K function and participation index. But you haven't lost the relationship, which is the nice thing. But there is a relationship, but they are not identical. So I take this minimum, 1.5, and this is what it will become. For other pairs, you can do similar things. Okay. So it has nice computational property. So this min actually gives you that anti-monotonicity. You can do the pruning. But the nice thing is that unlike support measure, which had no relationship with Pearson correlation coefficient, this case you do have a relationship. It's an upper bound in Ripley's cross-K function. So statisticians are not as offended. And for the domains which respect statistics, we are not out of the game right away. Okay? So here is an example. So in fact, so this one I can quickly show you what the values are. So first we can compute for something like this. So what do you think is participation index for A and B here? So if I go from A, out of the 3, how many can see B nearby? 2 out of 3. And if I go from B, 1. What's the minimum? 2. Okay. So this is cross K and this is the 2 by 3, right? Minimum of the 2. But cross K actually is more like cross product. So there are 6 possible edges, only 2 are present. So this is cross K, upper bound. Okay. If I am in this space, notice that any B I see a A, any A I see a B. So this saturates. Cross K has not saturated. Okay. And finally cross K saturates. So you can kind of interpret both differently. Okay. So basic difference is that in collocation we, instead of transactions, we use this notion of neighborhood graphs, and we create measures which are aware of spatial statistics, and they retain some amount of computational property. But these measures are far more expensive than these measures. Okay, each participation index computation is like a spatial join. Okay, so you are doing a whole bunch of spatial join. Okay. But the good news for us is that computers are becoming more and more powerful, so you can do better approximation of the world. Okay. So again, in data mining literature now there is a big following. There are hundreds of papers which have followed up on collocation. Some have tried to add statistical confidence measure to it. Some have taken it to time and so on. So it's a pretty well followed and mature kind of method. And I'm going to skip this as well. And we can do comparison. Let's not worry about it. You got the crux. There are different algorithms. As I said, spatial joins could be used to compute participation index, and in a database environment that makes a lot of sense because these are very, very optimized. But if you're writing custom algorithm, you don't like join, then you can also come up with algorithms which are working without join. Okay, and that's all I would say. I'm not going to worry. These have been extended for space and time. The basically neighborhood. This whole technique depends on how you define neighborhood. So neighborhood doesn't have to be just spatial distance. You can also do a time lag. And once you define the W matrix, everything carries through. Okay. And there was a projects where you can relate, events of this kind which are not exactly at the same time, but they are sort of spatially slightly separated, and there is a time lag. Okay. When we remember first day, I was even showing you for moving objects and stuff. You can do that. Okay. So let's pause here, quick minute for a review before we go to the tutorial. Okay. Okay, how many think A? Okay. All right, B. Okay, C. All right. Okay, and D. Okay, lot more. Okay, good. So this was just looking at that anti-monotone property. That's all. So so with this, we have at least given you a glimpse of this world, and a quick summary that why I'm arguing that you need to go beyond classical statistics, classical data mining, classical machine learning, and here are some summary messages. At the least, you should be aware of this implicit relationship. So a lot of spatial methods, they use the W matrix, right, the neighborhood relationship. So that matters a lot. So even if you love your machine learning and your deep learning, and that's okay, but even there, at least in feature selection, use some useful information about space, okay? Try to give neighborhood information or distance information. That's the least you should take from that, okay? Of course, if you can go beyond that, try to check whether your machine learning method is using independence assumption. If it is using that, think about how you can try to reduce that impact of that. Better yet, go to spatial statistical or spatial data mining method. If you are willing to go beyond that, even in these pattern families, think about, things like cost of false positive, okay? Or the impact of losing your neighborhood connection when you transactionize space, right? So you can actually do more custom methods, okay? So at every level, there are new challenges, and depending on your interest or the time, at least I would say do this, okay? But if you go a little bit further, will be great, okay? So this is sort of the end of discussion. Are there any quick questions before we switch, and have a small guest, lecture here, okay? So quick questions on generally spatial data mining or statistics. Okay, we are all ready? All right, good. So Professor Minch, this is, you have the stage, so.
Thank you, Professor Shaver. Yeah, it's been a privilege to have these lectures in this center because this is one hub of, geography, geospatial activities. Mr. Verghese is sitting behind, but then somebody in this center, here in JNU, we call it then schools and centers, as versus departments and faculty and etc. Yeah, so we do have Professor Ms. Lal Punia, who has an engineering background and has been in this center for a long time, and we would like Professor Punia to share your experience of you, because I think you have been on both sides of the border, and I think this will help us appreciate the hard work and challenges of the other side vis-a-vis our own, and in order to have crosstalks. Over to you.
Now, first of all, I would like to extend my thanks to Professor Shekhar that he spared his time and collaborated with our Department of Computers in JNU with Professor Minch, and this what we were discussing from last couple of years, and finally we are able to realize into a reality to having a spatial data analytics program in JNU. Now, coming back directly to what I want to talk about some work what we did a couple of years ago. 2004, Ministry of Agriculture has sponsored a project to Department of Space about mapping natural resources. And later on, that program was advanced to, like, we have enumeration of the population, that is Census of India. That was envisioned later on as a natural resource census. So from 2004 onwards, with the support from Ministry of Agriculture, Department of Space is generating information in terms of a digital database about various land use categories in India. Prior to that, there was hardly any program. So it means that we have a continuous data repository with us in terms of the data from 2004, 2005, that was the first cycle, which starts with the summer crop and ends as a giant crop. So it means from the monsoon, like June to October, and then November to April, when you harvest the rabi crop, and then finally there is a giant crop, what we call as a summer crop. So as you know, there are various data mining techniques which are there in terms of classifying the data. So we thought of coming up with a innovative technique that was available that time, was a decision tree approach, because various scholars and the art of technology that was available that time, it was the best technique to infer the information related to land use cover from various optical sensors that was on board various remote sensing satellites. Now, briefly, there are various kind of optical sensors which collect information, and they have different temporal resolution. Some satellites, they revisit the same place twice a day, whereas some satellites, they have a fortnightly temporal resolution. They visit the same area after 2 weeks. So it means you have a lot of information, terabytes of information flowing. It's really a very big data. Now, challenge is to classify that data and pass on the information to the decision makers so that they can take appropriate decision well in the time. Now, your technique, what you are going to apply for doing data mining, and finally, what you call data analytics, where you analyze the patterns. The patterns could be the pattern of similarity, it could be pattern of exception. This is very important. So we use decision tree approach there. Now, some of those who are from the application side and also those who are very fundamentally dealing from the computer side in the data, especially in the data. So I would like to urge you to also look into this particular domain where you have huge amount of data coming every day that can help you to analyze land cover information that has these, precisely in these contemporary times, have lot many implications for the environment as well as for the economy. So there's a one sensor that is called advanced WIFs, which has a spatial resolution of 56 meter. One image has about, say, 8,000 by 8,000 columns and rows, lot of data. But if you using it, say, around 8 images in a year to get your annual land use information. Annual land use information, I mean to say, you should have information about, say, state of Delhi, how much area that is an urban, which could be represented by impervious built-up area, how much area that is under forest, how much area that is under plantation, how much area that is under, say, current fallow, how much area that is in double crop area, how much area is there in a triple crop area, how much area is for the kharif crop. This information is very critical for the planning. Similarly, this information is also very critical, those who are enrolled or those who are actively participating in urban planning perspectives. Now, getting this annual land use information, so it means you require at least minimum which can cover this temporal variability across summer, winter, and the Jayad season. Now, as I said, your one image has about 8,000 by 8,000 columns, and then you have 8 images. So it means, and one image has about 4 layers. So you have about 36 layers with you, and you have to compute information, the information which is useful to you. So then you run a decision tree approach where you train your classifier. You train your classifier by giving them exact information, then in combination of these bands, if you're going to use. So what he was talking about, association rules. So your rules should be discrete, your rules should be minimum, and set of the rules can finally give you a classified map. And that classified information should be exact and should be accurate as per the requirement of the accuracy assessment, so that people, decision makers, have a confidence over other available classifiers. Now, as decision tree approach, as you know, that there is information is basically based on information game theory. It keep on splitting, what we call as a partitioning of the space, a recursive partitioning of the space, and finally it gives you leaves and the trees. And those leaves and the trees finally which are there, they are more homogeneous and where entropy is homogenized. But some of these statistical tools for the data mining gives you the information in such a way that you have n number of rules. You can finally come up with, say, 2,000 rules. But you need to prune them, and you finally need to get only the set of minimum rules which would be able to classify the whole image. So this is the one application area what we've published. I will share that paper later on. You can access it from Professor Minj. And this was work that we did published in 2011 and were involved in operational activity 2004, 2005, 2006. If you want to access the data sets which are available in the Bhuvan portal of NRSC, National Remote Sensing Agency, you can go there, and if you look at the areas of Haryana, Punjab, and And Delhi, you can get the data for these 2 years. This was extracted by using this particular decision tree classification approach. The second work we did in Kolar Taluk in Karnataka, where we compared their classification methods. Another one was like using multi-layer perception, what people also call multi-layer perceptron and decision tree approach, that was using MODIS data. As I said, there are various optical sensors. MODIS captures information about land use twice a day. Now you imagine how much data you have. All this analysis, data mining, was done on a desktop computer. But nowadays there is a requirement to do this is in a real time on the satellite sensor itself and transmit that information in a real time to the user. Now take an example, forest fire. Some sensors which are there, which are the thermal sensors, they can detect the forest fire as well as agriculture fire. That is what debated in India in the northern parts. That is called agricultural residue burning. Now that information need to be transmitted in a real time to the user so that they can take a remedial measure in a minimum response time, because fire is very critical. It can lead to disaster. So you can imagine from desktop computing, hard computing, now there's a requirement to do real-time computing and pass on this information by making use of the algorithms which are part of spatial data analytics. So we published a third paper in Current Science that was agricultural residue burning, where from the thermal data and also from the optical data, the burn scars were measured, and finally the area under agriculture burn scar was quantitatively corroborated. Now coming to the fourth point, I will quickly wrap up. There's another area which is of major attention these days is geovisualization. In geovisualization, there are three key words. One is a computer supported. Your application should be computer supported. It should be effectively graphically represented. And third thing, it should be interactive. It should be interactive. Computer supported means computer device supported, which includes your mobile phones as well, your handheld devices as well. And it should be interactive. Means one of the example you see these interactive animations where you can play with it. You can explore your data. You can synthesize your hypothesis. You can revisit your hypothesis. And then finally you can present it, which needs a lot of exploration. So geovisualization include these three keywords. Within geovisualization, there is similar kind of thing like spatial data analytics. Little bit you need to extend it, which is called visual data analytics, which is a lot of scope these years. Like Professor Shekhar was talking, you have transactions done using ATM all across the nation. Every ATM card has its unique ID. You can find out the pattern across India, what is the pattern of the consumer's habit. But it has to be done in real time so that you can take the remedial measures. There's a group in Germany headed by Professor Andrienko and Adrienko, both husband and wife. Initially, he was the first chairman of the Commission of Geovisualization. He contributed a lot to this visual data analytics, which involves spatial data analytics as its base. So another application they tried was that making use the information from our mobile devices. Most of our mobile devices these days are they are equipped with location-based sensors. The moment you invoke it, the service provider get the information, it's data logger. Now it's again, trillions of data is there with your service provider, which gives you information about your co-location. It gives the information how many minutes you are waiting on a particular traffic light. And it also gives the information to you how much time you spend on a particular road. That all information is used by these days by some of the big corporate companies like Google to give you real-time feeds for the traffic. But this information can also be used for the consumer behavior and also what is your everyday lifestyle. where are you going, how much time you are spending in a university, how much time you are spending in a mall, how much time you are spending on sports ground, how much time you are spending on a pub, how much time you are spending outside socializing people. So it tells about whole of your behavior, and which is these days is very important for social networking and social analysis. So there is a tremendous scope. When your data, the time when it becomes spatial, and you have whole fundamentals coming about database, if you integrate, you have capability of doing analytics. I think this is a big area which is coming already there in the western part of the world, but we need to strengthen our teaching as well as research activities, and a lot of scope. Let me tell you, most of the government flagship schemes, you name it, Pradhan Mantri Gramin Sadak Yojana for rural area, you name it, traffic behavior in an urban area, you name it, Rajiv Awas Yojana or housing for the poor in a city area. All these schemes, including Narega, all these schemes these days have a location attribute, and there is a tremendous data which is already available on NIC portals. The point is this: you have to envision, you have to think around, this perspective of database. You first harmonize your database, then apply these techniques which are being taught to you. So I would like to end with this, and I again want to thank Professor Shekhar. I myself wanted to attend this one, but somehow there are other responsibilities that we have to do, and I wish you all the best. Thank you.
Let's give a really big hand to Professor Punia, and thank you so much.
Okay, so we'll go to the tutorial, and I think we have two sets of exercises, so we'll distribute that. One is more conceptual and other is little bit technical. So let's work on that, and we I think have about 20-25 minutes. So let's spend maybe 10-15 minutes working, and then we'll publish the answer and discuss. Okay. Both, it is one more. So first distribute this, and there's another side. Can I keep one copy? Yeah. Yeah, this is the other one. So please distribute both, one each. I'll come